The central limit theorem gives us information about the sampling distribution of the sample mean. Remember that if you took every possible sample of size n from a population and found the mean of each sample, the distribution of those sample means is the sampling distribution of the sample mean. The central limit theorem states that when you draw a random sample from any population, as your sample size n gets larger, the distribution of the sample means will converge to a normal distribution. This is true for any type of population distribution, although populations that are less normal take larger sample sizes to become approximately normal. Using this information, we can establish a general rule that says that the sampling distribution of the sample mean is approximately normal if one of the following is true. Either n is greater than 30 or the data in the population follow a normal distribution. If the sampling distribution of the sample mean is approximately normal, then we can find and make use of the mean and standard deviation of that sampling distribution. The mean of the sampling distribution, mu sub x bar, is equal to the mean of the population distribution, mu. The standard deviation of the sampling distribution, sigma sub x bar, is equal to the standard deviation of the population distribution, sigma, divided by the square root of the sample size, n. If we're given a population mean, population standard deviation, and sample size, then even if we don't know the population distribution, we can use this information to find the probability of getting a sample mean in a given range. Here's an example that makes use of the central limit theorem. The weight of third graders is distributed with a mean of 75 pounds and standard deviation of 5 pounds. If we take a random sample of 64 third graders, what is the probability that the average weight of third graders is greater than 76 pounds? In this problem, we don't have any information about the shape of the distribution of third graders' weights in this region. However, we have a sample size of 64. Since the sample size n of 64 is greater than 30, we can apply the central limit theorem, which tells us that the distribution of the sample means is approximately normal. The mean of the sampling distribution, mu sub x bar, is equal to the population mean mu, which is 75. The standard deviation of the sampling distribution, sigma sub x bar, is equal to the population standard deviation, sigma, divided by the square root of the sample size, n. We're told that the population standard deviation is 5 and our sample size is 64. So we can substitute those values. Evaluating, we get a result of 0.625. Now that we have the mean and the standard deviation of our distribution, we can calculate a z-score corresponding to our sample mean. The z-score will be equal to our sample mean of interest minus the mean of our sampling distribution divided by the standard deviation of the sampling distribution. Since we're interested in the probability that the sample mean is greater than 76, we'll use 76 for the sample mean. Substituting the values we already calculated, we get 76 minus 75 divided by 0.625, which equals 1.6. So the probability that the sample mean x bar is greater than 76 is equal to the probability that z is greater than 1.6. A z-table gives us areas under the standard normal distribution to the left of a given value. To find the area to the right, we can use the complement rule and subtract 1 from the area to the left. In this case, we can find 1 minus the probability that z is less than or equal to 1.6. If we look at a z-table, we find that the probability that z is less than or equal to 1.6 is 0.9452. Evaluating, we get a final answer of 0.0548. Thus, the probability that the mean weight of a random sample of 64 third graders in this region is greater than 76 pounds is 0.0548, or 5.48%.